So this is example 6.3. This is what you see on Canvas, but this is the one I want to ask, which is this guy. So this guy has been modified than the one on Canvas. Okay, so I'm going to say that this is the one that's on Canvas. It's the same question, but this one has more of the situation that I would ask you on a quiz or an exam. So let's go look at that. So it says example 6.3, a small 100-gram cart is moving at 1.20 meters per second on an air track when it collides with the larger 1.00 kilogram cart at rest. After the collision, the small cart recoils at 0.85 meters per second. A, sketch the situation, draw a momentum bar diagram in which object has the largest momentum. And then, of course, we want to verify that. And then finally, B, what is the speed of the large cart after the collision? So A has a lot of stuff on there. So let's start looking at this. So what we want to do is that if we're talking about an elastic collision, the first thing that you gotta ask yourself is it equal masses? Is it a massive target? Or is it a massive projectile? So you gotta figure out which situation it is. So the way we want to do this here is that we assume an elastic collision, which then means you must determine if M1 is equal to M2, is M1 greater than M2, or is M1 much less than M2? Which situation do we have? So just looking at our numbers, we could see here is that our projectile which I'll define as M1. This guy is 100 grams, so it's 0.1 kilograms. If I look at our larger cart, this is our target cart. And if I look at this guy here, I'm going to call that M2, and you could see that this is 1 kilogram. So immediately what this tells me here is that M2 is equal to 10 M1. So we're going to say here is that M2, I would say, is much bigger than M1. So right away, by us looking at this situation, we know what we should expect physically. So then I'm going to come back here, and you could see that this is a massive target. So that means my bar diagram has to behave something like this. So we want to look at the details of this. So now I know I have a massive target. So now this is closest to a massive target. So then here we go. So now let's start drawing our pictures. And we want to ask detailed questions, right? We want to ask detailed questions. So here I go. I have a block. Here's my block coming in. I have my block. It has this amount of momentum. So my projectile has a small mass, and then I have a bigger block. And this guy is initially at rest. So I got to ask detailed questions. So then I ask, what do I know about the system? If I include both of these particles, we see that the only force, the only forces are internal. There are no external forces. So then that means that J impulse is equal to 0, which then tells me right away that P total has to be a constant. So I can use conservation of momentum. Now, using our sign convention, I'm going to say that this is my negative direction here. This will be my positive direction. So what do we expect? This is a lot like the golf ball, bowling ball. So we expect the golf ball to bounce off, and it's going to have a momentum, P1 final, that's now in the negative direction. And what this is really telling us here is that we expect that P1 final should be approximately equal to P1 initial, that the golf ball bounces off the bowling ball at roughly the same speed. The momentum of the bowling ball is now going to be moving to the right. So we expect the speed of the momentum, again, we expect that V2 final is very small, that the golf ball is barely going to move. So what does the bar diagram tell us here now? So if I look at the bar diagram, so now if I look at my bar diagram, what do I expect to see here? Well, I would expect that I have 2 blocks of initial momentum coming in like this. And what we say here is that if this is our 0 point right here, this is going to be our positive direction. This is going to be our negative direction. So everything going to the right should be above the line. Everything going to the left should be below the line. So when I look at this thing, I see here that the momentum of the big cart starts off at 0. Therefore, the system must adjust to keep this total momentum a constant. So what do we expect? We expect that the golf ball loses some speed, but it keeps its speed relatively the same. So as the bowling ball gets more and more massive, then the speed of the golf ball gets, closer and closer to the exact same value that it came in. And then what this tells us here, that then the momentum of the bowling ball, it has to stop the initial momentum, and then it has to increase to speed up the ball again. So therefore, the lion's share of the momentum has to be with the bowling ball going to the right. So from this picture here, from our bar diagram, what do we know here? Well, there's two things that we got to check. The first thing that it says here is that we expect that the momentum to be roughly the same before and after the collision for the projectile, right? So this should, so in other words, this is telling us that they should be roughly the same. And again, if we ask the question why, it's because M2 is equal to 10 times M1. If M2, so in other words, this ratio is equal to 10. So as that ratio gets larger and larger and larger, then P1 initial then becomes identical to the absolute value of minus P1F. And the other thing that we see here is that the momentum of the bigger cart has to be larger than the momentum of the incoming momentum. This tells us that the outgoing outgoing target cart has a, I don't want to say much, has a larger momentum than the one coming in. So we got to check those. So how about if we check the first one here? Okay. You know, actually, I'm going to need, we have to calculate P2, right? The speed of the bowling ball first. Maybe we should calculate that first here. Well, I have it in order here. So let me stick to the way I have it here. So let's calculate the first one. So let's compare P1 initial versus the absolute value of P1 final. So let's calculate. So what we want to do here is that we want to calculate individual momentums. So the first one here is that I'm going to go P1 initial is going to be the massive one times V1 initial. So what do I know? I know that the massive one is 100 grams, so it's 0.1 kilograms, and its initial speed going to the right here is 1.20 meters per second. So if I plug in those values, I'm going to get 0.1 times 1.2, and I'm going to get kilograms meters per second, and this will give me 0.120 Newton second, and this would be the initial momentum. Now, what happens after the collision? If I look at P1 final, absolute, this will then be M1 V1 final, but V1 final we already is given as 0.85 meters per second. So if I plug in these numbers here, and this will be a Newton second, this will then give me 0.8, oops, no, 0.085 Newton seconds, and this will be P1 final. Let me be careful now. It's going to be the absolute value of P1 final like this. So then the question, how do they compare? Well, let's say that let's make a rough estimate. So we want to make a rough comparison by looking at one sig fig. So if you look at one sig fig, we could say that P1 initial, which is equal to 0.120 Newton second, this could be effectively, that's going to be 0.1 Newton second versus minus P1 final. This is 0.085 Newton second to 1 sig fig. Well, that's like 0.09. I could then say that this is roughly going to be 0.1 Newton second. So you can see here is that they're comparable, right? So when I'm looking at this guy right here, and I'm looking at that guy, very roughly they're comparable. In other words, that the speed of the ball coming in is equal to the speed of the ball coming out, roughly. But it's not the same. That looks like, but I mean, of course, they're not the same. That's only to 1 sig fig. I would assume here is that if I look at the ratio of P1 initial to minus P1 final, I would guess that that looks like, that's like about 1.7. Is that right? No, I don't know what that is. What is that number? I didn't calculate that number. Let me calculate this just so that we see. So I would get I get 1.4. Yeah, so you can see that this is about 1.4. And it's in the ballpark. They're still pretty close. Now remember, the bigger the ratio of masses, the better value that you're going to get. So now what we got to do here is that we need to calculate V2 final using conservation of momentum. Now we've already done that. So if I just come up here, I'm just going to go by my bar diagram. So if I use conservation of momentum, here's what I have right here. So this is my equation. So now, if I now look at this mathematically, what do I see here? This tells me that I get P1 initial plus P2 initial. Now remember that 0 is then going to equal to, look at P1. P1 final is negative P1 final plus P2 final. This minus sign is important. It tells us that it's there. So now, if I rewrite this whole thing here, then this will be M1 V1 initial. Look what I'm going to do. I'm going to bring this over to the other side. So I'm going to get minus, I'm going to get plus M1 V1 final. And that's got to be equal to M2 V2 final. So what I got to do here is I got to isolate V2 final. So now, isolating V2 final, you could see here is that V2 final is then going to be M1, V1 initial, M1 final, divided by M2. So look what I did here is I pulled out M1 from the left side. So now if I put this all together here, this is then going to be 0.1 kilogram divided by 1 kilogram plus the speed values. The speed values then read 0.12 plus 0.085, and I'm going to get units of meters per second here. And if I compute that, I'm going to get a speed of 0.205 meters per second for V2 final. So this is what the question is asking. And that's the speed of the big cart here. So now, does this make physical sense? Well, one, we said that P2 final had to be bigger than P1 initial. Is that true? Let's go check that out. So if I calculate P2 final, we see here that P2 final is going to be M2 V2 final. So this will then be 1 kilogram times the speed of 0.205 meters per second. This will then give us a value here for momentum, at least, that this guy is then going to be equal to 0.205 Newton second, or I can approximate that to 0.21 Newton second. So this is the momentum of the big cart, or of the bowling ball, if we could say that. So now, if I compare P2 final, you could see here that this is 0.21 Newton second. This guy is clearly bigger than the initial momentum, which is equal to 0.10 Newton second. It's almost twice the value, right? You can see here is that this is almost twice the value. In other words, if I look at the momentum and I look at this ratio, you could see here that this is 0.21, this is 0.12. I'm getting roughly 1.7. Well, that would be equal, but this is approximately almost twice. So that means that the outgoing momentum with the large cart is almost twice as much as what came in. So it's agreeing with what we're talking about. The lion's share of the momentum stays with the system going to the right. And furthermore, what about the speed? What about the speed of the large cart? What we said up here is that we expected the speed of this cart to be quite small. Is it? Let's look at the speed. So the speed of the incoming cart, right? This is the speed of incoming cart. This guy was equal to what was that speed? I think it was 1.20 meters per second versus the speed, the final speed of this is the speed of outgoing cart. That's 0.21 meters per second. So you could see that this is 6 times slower. It's 6 times slower. So it agrees with everything that we've talked about when we started dealing with elastic collisions. Okay, that's the end of that example.